Okay, in this video we're going to look at another way of solving a system of equations. This is going to be using something called Gaussian elimination. So the first thing we're going to want to do is write a system of equations as an augmented matrix. A system of linear equations can be represented as an augmented matrix. So for example, we have a system of two equations and two unknowns, a11x plus a12y equals a13. And then the second equation, a21x plus a22y equals a23. And so all the a's there are just coefficients there. So as an augmented matrix, basically we drop all the variables, and then instead of an equal sign, we have this kind of vertical line here. And then we have a column for x, column for y. And sometimes books will call this a 2x3 matrix. Or they may call it a 2x2 because you're solving a system of two equations and two unknowns. So sometimes it's referred to as a 2x2. So just keep that in mind if you're looking at other videos or whatnot. Same goes for a system of three equations and three unknowns. So you'd have a column for x's, a column for y's, and a column for z's. And then you have that equal sign again there. So we're going to go through the process for solving using the Gaussian elimination for solving systems of equations. Okay, so we're going to have something called row operations. So there's three row operations we're going to perform. The first row operation is we can interchange two rows. So the row operations, we won't do anything with columns. The second thing we can do is we can multiply any row by a non-zero constant, and then we can, and after we've multiplied it by that non-zero constant, we're going to replace that row with whatever we multiplied it by. So for example, if we multiplied a row by 5, then we would write the new row with after we've multiplied it by 5. So we'll do that replacement there. And then finally, we can add a constant multiple of one row to another row to replace it. And so that's kind of like the elimination method when we're solving a system of equations without matrices. So add a constant multiple of one row to another row to replace it. And so these are the three row operations that we're going to follow for Gaussian elimination. So we're going to do a little bit of illustration of what each one of these looks like, both with a system of equations and also with the matrix. So we're going to do a row interchange, or you can call it a row swap if you want. So here we'll take the system of equations, 2x plus 2y equals 16, and x minus y equals 4. If we wanted to do a row swap, basically what it's doing is you're rearranging the two equations there. Okay, so you're writing the bottom equation on top and the top equation on the bottom. That's what a row change is. So what it looks like with a system of equations is we go ahead and we drop the variables. So 2, 2, 1, and minus 1 are the coefficients for the x's and y's. And then on the other side, the equal sign is 16 and 4. The way we go ahead and write this is row 1, and then we use a double arrow like that. That means to interchange or swap row 2. And so all we do is we interchange the two rows. So the bottom row was 1, negative 1, 4, and the top row was 2, 2, 16. So we just change those. Some books will use the big uppercase R and lowercase r in different contexts. So there's nothing wrong with doing as lowercase. So usually what I like to try to do is have the uppercase be reserved for what is being replaced, or in this case, two rows are being replaced. They're being replaced with each other. So that's what interchanging two rows is like. Usually when we use this when we're doing Gaussian elimination is to avoid dealing with fractions. We may or may not be able to avoid fractions, but we do try to do that to eliminate having to deal with fractions, and it's an easier step to do a row swap than it is the other two operations. Okay, so let's do it. Go ahead and do an example of multiplying a row by a non-zero constant, and we're going to be interested in making zeros and ones, and this is the operation we're going to do to make ones, along with row swaps sometimes. Okay, so here's what it looks like with a system of equation. 4x minus 4y equals 16. 2x plus 2y equals 16. And so we'd probably want to solve this system by elimination. So we'd probably want to multiply the second equation there by 2 to solve by elimination. We're going to do this to try to illustrate what it would look like in a system of equations. So the process of Gaussian elimination, we're going to want a 1 in the upper left-hand corner. So that can be accomplished by multiplying the top equation by 1/4. And that's the exact same thing as dividing by 4. So 4 divided by 4 is going to be just a 1x there. 4y divided by 4 is y. 16 divided by 4 is 4. And then we write the bottom equation unaffected there. Okay, so that's what it looks like as a system of equations. So what does it look like if we're using an augmented matrix? So we'll start off writing our system. 4, negative 4, 16, 2, 2, and 16. And so we want a 1 right here. That's kind of our first thing, and we'll go through that in detail a little bit later. So here we're just practicing the row operation. We're going to make that a 1 by dividing by 4 or multiplying by 1/4. So 1/4 row 1 replaces row 1. Or in other words, if you'd like, you can go ahead and do row 1 divided by 4 replaces row 1. So then we divide everything in the top row by 4, so it'll give us 1, negative 1, and 16. Oh, sorry, not 16. 16 divided by 4 would be 4. And then the bottom row is unaffected. Okay? So that is multiplying a row by a non-zero constant to replace it. So that's what we use to make 1s in the Gaussian elimination, or Gauss-Jordan elimination. And then the last row operation here is to add a constant multiple of one row to another, and a non-zero multiple. If we can add a zero constant multiple of another row, but that doesn't change anything. So we want to do a non-zero constant multiple of one row, and we're going to add that to another row to replace it. And that is going to be for making zeros. So this is how we make zeros in the Gaussian elimination. So this is like the elimination method here. So we'll take the system of equations, x minus y equals 4, and 2x plus 2y equals 16. Now, if we're going to solve this by the elimination method, probably the easiest thing to do is to eliminate the y's. And so we'll multiply the top equation by 2. Well, I said probably the easiest would be to eliminate the y's. I will go ahead and eliminate the x because that follows the Gaussian elimination a little bit better. So we'll eliminate the x. We'll get the same answer if we eliminate the y's, but we'll model this out after the Gaussian elimination. Okay, so that's going to give us negative 2x plus 2y, and that's equal to negative 8. And then the bottom equation is 2x plus 2y is equal to 16. And then we'll add. So the x's will absorb, and we have 4y is equal to 8. Okay, so then how we do this with Gaussian elimination is the top equation was used, but it was not changed. So we used it, but we did not change. We only changed the bottom equation. So the top equation is still x minus y equals 4. But the bottom equation is now the new one we got, the 4y equals 8. And then we would solve that using back substitution. So you would solve for the y, and get y is equal to 2, and then you'd plug it into the top equation to find the x there. So here's what it looks like with an augmented matrix. So we have 1 minus 1, 4, 2, 2, 16. And so what we're going to do is we're going to make a 0 right here. That's in column 1, so you're going to use row 1. The opposite of 2 is negative 2. So we're going to do negative 2, and we're using row 1. Whoops. I hit the wrong button here, so let's go back a little bit. So we're going to do negative 2, row 1, plus row 2, and that's going to become the new row 2. So we can do the computation in a little table here. So negative 2 times row 1 will be negative 2, 2, and negative 8. We're going to add to it row 2, which is 2, 2, and 16. Our new row 2 will be 0, 4, and positive 8. Okay, so our new row 2 is 0, 4, and positive 8. And we did use row 1, but we did not replace row 1. We only replaced row 2. So row 1 is 1, minus 1, and 4. Okay. Okay. So now we're going to take a matrix and we're going to do some row operations with it. Oops. All right. So we're going to be given this would represent a system of 3 equations and 3 unknowns, or we can call it a 3 by 4 matrix. And the two matrix row operations given are -2 row 1 plus row 2 to replace row 2. So we're going to go ahead and take row 1 and multiply it by -2. So it gives us -2, 2, -2, and -16. Row 2 is 2, 3, -1, and -2. And our new row 2 is 0, 5, -3, and -18. So we'll go ahead and write that there. Okay, and then they're going to give us another row operation to perform. So it would be -3 row 1 plus row 3 replace row 3. So we're going to do the same thing. We're going to take row 1 and multiply it by -3 this time instead of -2. So it gives us -3, 3, -3, and -24. And then we're going to add to it row 3. 3 minus 2 minus 9 and 9. And our new row 3 is going to be 0, 1, minus 12, and minus 15. We'll write down our new row 3. Okay, and we'll write row 1 at the top. So row 1 was not changed by our 2 row operations. We did use row 1, but we didn't change it. We only replaced rows 2 and 3. So row 1 is unaffected here. Okay, and that is actually 2 of the steps of the Gaussian elimination. We'd have probably 2 or 3 more steps to perform there to be completely done with the solving by Gaussian elimination. Okay. All right. So Gaussian elimination, we're going to put it in row echelon form. There's also something called reduced row echelon form. So you might see some videos for Gauss-Jordan elimination, which is a little bit further. We'll use Gauss-Jordan elimination for finding the inverse matrix of a 3 by 3 matrix. So what what reduced what row echelon form is, is main diagonal of 1s, and then below that is going to be 0. So here's your main diagonal of 1s, and then below that is all 0s. Okay, and so then we can read our equations off of this. So this is your x and your y. So this says 1y is equal to b, and then the top equation says 1x plus c times y is equal to a. And then, so we know what y is equal to, so we just plug it back into the top equation and solve for x. Same goes for a system of 3 equations and 3 unknowns. We have here x is equal to z, and then the next equation, y plus fz is equal to b, so we can back substitute in for z and solve for y, and then we can back substitute again to find the x using back substitution in Gaussian elimination. So let's try it out on a couple. Well, I guess before we do that, here's my steps for a 2 by 3 augmented matrix or a 2 by 2 system. We're going to follow this pattern here, make a 1 here, a 0, and then a 1. That's your coefficient matrix, so then you'd have your augmentation line, and then you have some numbers here. Okay, so the first thing we want to do is write the system as an augmented matrix. And then what we're going to do is we're going to divide row 1 by A11, or multiply it by the reciprocal 1 over A11, and replace row 1. And that's going to make a 1, provided that A11 is not 0. If it's 0, then we want to probably do a row swap. Okay, the next thing we're going to do is we're going to make a 0 right here. And so to make a 0 there, that's in column 1, so we're going to use row 1. And so we're going to use the opposite of A21 to eliminate this term here. So negative A21 times row 1 plus row 2 will replace row 2. Okay. Then the next thing to do is to make a 1 here. So we're going to multiply that row by the reciprocal of A22, or you can think of it as dividing by A22, provided that A22 is not 0. And then once we've done that, we'll use back substitution. Okay, so now I think we're going to go ahead and see this in practice. So here's our pattern to follow. And so the system we're going to solve here is right here. And then we're going to go ahead and write it as an augmented matrix. And they're going to ask us to use Gaussian elimination. So as an augmented matrix, 1 minus 3, 3, 3, 5, and negative 19. So we do have a 1 here. So we got 1 step for free, so we have 2 more steps to do. So we want to make a 0 where that 3 is, and that is in column 1, so we're going to use row 1, and the opposite of 3 is negative 3. So we're going to do the row operation negative 3, row 1, add that to row 2 to replace row 2. So negative 3, row 1 will be negative 3, 9, and negative 9. Row 2 is 3, 5, and negative 19. And then we'll go ahead and add to make our new row 2, 0, 14, and negative 28. 0, 14, and negative 28. We did use row 1, but we did not replace row 1, so row 1 is still itself. Okay. All right, so we got 1 more step to do, and we would like to make a 1 where this 14 is. So to make 1s, we're going to divide by, in this case, 14, or multiply by 1 over 14. So we're going to do 1 over 14, row 2 to replace row 2, or you can think of it as row 2 divided by 14, and that'll be the new row 2. So dividing all of those by 14, so 0 divided by 14 is 0, 14 divided by 14 is 1, minus 28 divided by 14 is minus 2, and row 1 is itself. Okay? So the top equation represents x minus 3y equals 3, and the bottom equation represents y equals negative 2. Okay, so now we're going to back substitute x minus 3 times, and then y is negative 2, and that's going to equal 3. Okay, so then negative 3 times negative 2 will be positive 6, so we're going to subtract 6 from both sides, and we're going to get x is equal to negative 3. So our ordered pair here as a solution is negative 3 and negative 2. Okay. All right, and we've performed the Gaussian elimination. Let's go ahead and do a couple more of 2 by 3 as an augmented matrix, or a system of 2 equations and 2 unknowns. Okay, so here's our pattern we would like to follow. And here's the system that we want to solve. And the first thing we will do is write it as an augmented matrix. Okay. And so now we would like to make a 1 where this 2 is. Okay. So on one hand, you can divide the top row by 2, and that will certainly work. Sometimes we may not want to do that if I'm going to end up with fractions or a messy decimal or something like that. But what you also notice is you have a 1 here. So it might be easier to do a row swap. So we're going to go ahead and do a row swap. So we're going to swap rows 1 and 2. 1, 2, negative 3, 2, negative 6, and 4. And so that accomplishes the first step without doing any sort of computations. We switch the rows. The next thing we want to do is we want to make a 0 here. This is in column 1, so we're going to use row 1, and the opposite of 2 is negative 2. So we're going to do negative 2, row 1, plus row 2, replace row 2. Negative 2, row 1 will be negative 2, negative 4, and 6. Row 2 is 2 minus 6 and 4. We'll go ahead and add and get 0, negative 10, and positive 10. So that is our new row 2, 0, negative 10, positive 10. And then the top row was used, but it was not replaced. Okay, so we've got one more step to do here for Gaussian elimination, and that is to make a 1 where this minus 10 is. So we're going to divide the bottom row by negative 10. So negative 1/10, row 2, replace row 2, or row 2 divided by negative 10, replace row 2. Okay, so that'll be negative 10 into 0 is 0. Negative 10 divided by negative 10 is 1. 10 divided by negative 10 is negative 1. And the bottom row, the top row is unaffected. Okay, so the bottom equation says y equals negative 1. Top equation says x plus 2y equals negative 3. Go ahead and do your back substitution. So y is negative 1. So you have x plus 2 times negative 1 is equal to negative 3. Add 2 to both sides. And we have the solution, x is equal to negative 1. So our ordered pair is negative 1 and negative 1. Okay. So I think I have two more solving systems, two equations, two unknowns by Gaussian elimination. So let's see what we got going here. All right, so we'll write down our pattern, and then we'll write down our system. Okay, and then write it as an augmented matrix. Okay. All right, and the first thing we'd like to do is we'd like to make this a 1. And so I don't have a really good row swap here. I'm going to have the same problems. So we're going to divide the top row by 2 or multiply it by 1/2. And so we'll get a fraction, and it happens. Sometimes it's unavoidable. So dividing, so 2 divided by 2 is 1. Negative 3 divided by 2 is negative 3/2. And then 12 divided by 2 is 6. Bottom row was unaffected. Okay. Next thing we'd like to do is we'd like to make this a 0. This is in column 1, so we're going to use row 1. The opposite of 6 is negative 6. Negative 6, row 1, plus row 2 replaces row 2. Okay. So negative 6, row 1 will be negative 6, 9, and negative 36. Row 2, 6, negative 9, and 36. And then we'll go ahead and add, and we get 0, 0, 0. All right, so what in the world does that mean? Okay, so the bottom equation says 0 equals 0, and the top equation says x minus 3y, 3/2 y, pardon me, is equal to 6. Now, 0 is equal to 0. That's a true statement. And so what this means is the two lines were actually the same, so this is an infinite solution. As, all points on the line is a solution here. So we have infinitely many solutions. So it's the set of x, y that live on the line. Okay, so that's how we say it's the set of all points that live on the line there. Infinite solutions. Okay, so let's go ahead and look at the other scenario where we get a bunch of zeros. So we'll write down our pattern to follow. And then we'll look at almost the exact same system of equations here, but we're going to change one number there. Okay, we'll write our system. Divide the top row by 2 or multiply it by 1/2 and replace that top row with that result there. So 1 minus 3/2 and 6. Bottom row is 6 minus 9 and 10. We'd like to make a 0 here. That's in column 1, so we're going to use row 1, and the opposite of 6 is negative 6. So we're going to do negative 6, row 1, plus row 2, and that's going to replace row 2. So negative 6, row 1, negative 6, 9, and negative 36. Row 2 is 6 minus 9 and 10, adding those. 0, 0, and minus 26. 0, 0, minus 26. The bottom equation says 0 equals negative 26. And the top equation says x minus 3/2 y is equal to 6. 0 is not equal to negative 26. That's a false statement. And so that means this is a no solution. Okay. So in fact, these two lines were parallel. So we had parallel lines, don't intersect. So when we're solving either by graphing or elimination method or substitution method or any matrix method, we're going to get a no solution here. Inverse matrix method we'll not quite know what's going on. It'll be either infinite solution or no solution, but we'll get into the inverse matrix method in the next video. Okay, so I think that was the last of the systems of two equations and two unknowns. So here's Gaussian elimination for a augmented matrix as a 3x4, or if we're looking at it as a system, it's a system of three equations and three unknowns, so it's sometimes called a 3x3. So first thing you're going to do is you're going to write the system as an augmented matrix, and then you're going to make a 1 in the upper left-hand corner. So you're going to multiply row 1 by 1 over A11, provided that A11 is not 0. Then you're going to make zeros in the rest of column 1, so you use row 1. So you do negative A21 row 1 plus row 2, replace row 2. So that gets you the 0 in the right there. And then A31 row 1 plus row 3, replace row 3. That'll give you the 0 right there. So that takes care of the first column. Then in A22, we would like that to be a 1, so we multiply by the reciprocal and replace row 2 with that, so that gives us the 1 here. Okay, and of course, provided A2 is not 0. Then we would like to make a 0 here, so that's in column 2, so we're going to use row 2, so we're going to do negative A32 row 2 plus row 3 to replace row 3. That gets you the 0 there. And then the last thing here is we want to make a 1 in that position there, that's in row 3, so 1 over A33 row 3 to replace row 3. Okay, and then after we've done that, we'll use back substitution. So let's go ahead and see what we got going. So we are going to solve this equation here, this system of equations here. We'll write down our pattern. Okay, and then write it as an augmented matrix. And we got the first step for free. You see we have a 1 there, so that's good for us. Less work for us to do. The next thing we'd like to do is we'd like to make a 0 here and a 0 here. Those are both in column 1, so we're going to use row 1. Okay, and we're going to do negative 2 and a negative 3 for rows 2 and row 3, respectively, to get those zeros there. So we're going to do negative 2 row 1 plus row 2 to replace row 2. So negative 2 row. So we're going to do negative 2 row 1. So that's going to be negative 2, 2, negative 2, and negative 16. Row 2 is 2, 3, minus 1, minus 2. Row 2, the new row 2, 0, 5, negative 3, and negative 18. 0, 5, negative 3, and negative 18. And we'll do negative 3 row 1 plus row 3, and that'll replace row 3. So negative 3 row 1 will give us negative 3, 3, negative 3, and minus 24. Row 3 is 3 minus 2, minus 9, and 9. New row 3 will be 0, 1, minus 12, and minus 15. 0, 1, minus 12, and minus 15. And we did use row 1 for both of those row operations, but we didn't replace row 1. We only replaced rows 2 and 3. So row 1 is row 1. Okay, so we are done with the first column. So the next thing we'd like to do is we'd like to make a 1 here. Now, you certainly can divide everything by 5 in that second row, but we're going to have a bunch of fractions. Sometimes that's unavoidable. Sometimes we can do a row swap. We don't want to mess with row 1. We don't want to move it anymore because we have that 1 there. If we move that, then that puts the 1 down here, and we don't want to do that. So leave row 1 alone in terms of moving it. But we can move like rows 2 and 3. And so that's what we'd like to do. We'd like to perform a row swap, and that'll get that 1 up there. So we're going to perform a row swap between row 2 and 3, or a row interchange. Okay, so we perform the row interchange. And that gives us the 1 that we desire here. The next thing we want to do is we want to make this 5. We would like to make that a 0. That's in column 2, so we're going to use row 2. The opposite of 5 is negative 5. So we're going to do negative 5 times the row we're using, which is row 2. Negative 5, row 2. Add that to row 3 to replace row 3. Negative 5, row 2 will be 0, minus 5, 60, and 75. Row 3 is 0, 5, negative 3, and negative 18. New row 3, 0, 0, 57, and 57. So this looks like it was rigged to be pretty nice. New row 3, 0, 57, 0, 0, 57, 57. Okay. And then there is row 2 and row 1. Okay. So we've gotten almost done there. We've taken care of the first 2 columns. The last thing we got to do is we need to make this a 1. So we're going to divide row 3 by 57. So 1 over 57, row 3 to replace row 3. Row 3 divided by 57, replace row 3. 0, 1, 0, 0, 1, 1. Okay, then write down the rest of the matrix. And then we're ready to do some back substitution. The bottom row says z equals 1. And then the next row says y minus 12z is equal to negative 15. And we'll go ahead and back substitution. So y minus 12 times 1. So that'll just be y minus 12 is equal to negative 15. And if we add 12 to both sides, that gives us y is equal to negative 3. And now we're going to back substitute both of those into the original, or not necessarily the original equation, but the top equation. X minus y plus c is equal to 8. So that is x minus negative 3 plus 1 is equal to 8. So that becomes x plus 4 is equal to 8. So x is equal to 4. So we have the solution 4 minus 3 and 1. Okay. I think we're going to look at 2 more kind of like special cases here. What else can happen here? Okay. So I'm not going to write down everything, the whole process here, but let's suppose we went through and we were solving something very similar to the previous one, and you see how we got a bottom row of zeros. So 0 equals 0 is true, so we're going to see what we have left. So we have y minus 12z is equal to negative 15, and then we can solve that for y, so we can kind of come up with a way of describing the solution. So this is going to be an infinite number of solutions. Because it's a system of 3 equations and 3 unknowns, it's actually intersection of planes, and so planes can intersect on lines. So we want a way of describing that line. So if we solve for y, we get y is equal to 12z minus 15. If we take the top equation there, x minus y plus z is equal to 8. And there's different ways of writing this. So you could also take that second equation and solve for z, but that's a little bit more difficult. So here it's easier to solve for the y. Okay. Now that top equation, we're going to go ahead and solve that for x, because we're going to write our solution in terms of z. So x is equal to 8 plus y minus z. Now we have a value for y, so we'll go ahead and plug that in. So that's going to be x equals 8 plus 12z minus 15. Okay, so x is going to be equal to what happened here? We forgot a z, didn't we? Well, let's put that z in there, right? So 8 plus y was 12z minus 15. Oh, yeah, we sure did. All right, so we forgot the poor z there. So 12z minus a single z should be an 11z. Okay. And then 8 minus 15 is 7. So our solution is going to be all ordered pairs x, y, and z, such that the following: x is going to be equal to 11, z minus 7, and y is equal to 12z minus 15. So that is all possible ordered pairs. So it's probably going to be it is going to be a line in 3 dimensions where these 3 planes actually are probably going to be intersecting here. All right, let's go ahead and look at the other special case. So let's say we run into something like this, okay? And so the bottom equation says 0 is equal to 5, and that's false. That's no solution, and that's it. We don't go any further. Okay, so that is Gaussian elimination. A number of examples, and I think we've done plenty for this video. So we'll see you next time.